So first of all, there is a common terminology used in the NFV world. It is called Enhanced Platform Awareness, or EPA. EPA is covering a collection of different mechanisms to get the most of from a generic server, instead of having to use a dedicated, specialized, even proprietary hardware to get some extra performance in a server. So EPA features consist on changing the size of memory paging, on dedicating CPU cores to virtual machines, and making these virtual machines aware of the topology of the CPUs of the server, using dedicated physical interfaces for virtual machines instead of virtual interfaces, and things like that. All of these techniques are available since a long time ago in the kernel and in operating systems used in data centers. So they can be controlled by a VIM, requested and configured by the VIM, and they can be at a higher layer of orchestration where we are using open source MANO. They can be also orchestrated from there and requested to the VIM. So if the VIM/NFVI infrastructure supports EPA techniques, then open source MANO is able to request them and implement them in the VMs through modifying the descriptors to specify that you need these techniques to be used. So I'll be going briefly through each technique. There is a dedicated slide about each, I guess, but briefly, huge pages, instead of allocating the default size of the pages when looking up information in a RAM memory, it assigns larger pages for the virtual instances so that we avoid cache misses, and then this has a better performance related to the CPU that is used to look up information. CPU pinning also impacts CPU. It's when you instantiate a virtual machine, by default, the hypervisor is assigning CPU resources dynamically, so you don't know exactly where your VM is at any given time. With CPU pinning, you specify which, or to use a single set of CPUs, or even you can give the number of the CPU specifically to the virtual machine. So instead of moving dynamically, it will be pinned, and this impacts performance positively. Non-uniform memory access topologies are topologies that have a memory space dedicated to the CPU, and this is called a node. The physical set or group of CPU memory interfaces resources are separated in different nodes. So you can make the virtual machine aware of this topology of multiple nodes inside the server, so they can leverage, for example, having CPU and memory in the same node instead of having to go through interconnect, which will bring slower times when reading memory. And SRIOV, or pass-through techniques, will allow us to connect a virtual machine directly to the NIC instead of going through a virtual switch. So yeah, this is this is a bigger diagram just to show that you can pin virtual machines in specific cores. You can let them access local memory instead of going through an interconnection between nodes in a server. So everything here is how you leverage the physical resources that you get in any given server. so that you can increase the performance of your VMs. When you launch a VM like we have been doing this week, you don't have any guarantee that it will have a CPU here and a CPU there, and a read memory from a node to the other node. And of course, we are using virtual interfaces, so everything goes to a software switch. So everything that I've mentioned impacts the performance, and you won't get the data rates that you expect, for example, or the calculation you need. You would need to assign a lot of resources, and you still will hit a bottleneck. With these techniques, you can increase performance significantly. Okay, same thing for memory huge pages. It's a matter of increasing the paging. And there's a caveat here. So when you enable CPU pinning or NUMA topology awareness techniques, you just request them, and that specifies OpenStack how to assign CPUs to the virtual machines. And that's can occur in a dynamic way. But to change the paging of the RAM memory, that requires a reconfiguration at the server. So that usually requires to reboot the physical server. So to have a huge pages pool, for example, if you got here 72 gigs of RAM, you can say, okay, I will leave 24 of those gigs to regular paging and 48 for huge pages. And if you start adding virtual machines that request normal pages, then you will have a hard limit of 24. When you exceed that, then you will receive an error because the system cannot assign a huge page or huge paging to a virtual machine that is not requesting it. And the other way around too. If you request huge pages and you don't have enough memory in your huge pages pool, then your virtual machine is not being able to be launched. So this distribution here has to be planned carefully to be able to allocate the virtual machines that request huge pages and the virtual machines that request normal pages. And specifically because each change requires a reboot. So obviously, we don't want to be rebooting the nodes. So in production environments, there are some servers dedicated to huge pages and some others dedicated to normal paging, usually. SROV with SROV, so as I mentioned, you can connect a virtual machine instead of going through a layer 2 virtual switch, like for example, Open vSwitch or a Linux bridge. It will, and then go into the NIC, it will go straight to the NIC. So it will see its interface inside the virtual machine as the regular NIC, and it will need to support the driver of that NIC to be able to send traffic over it. We also and this SROV, that the special thing about it, as compared to pass-through, is that you get a virtual PCI address, so you can actually put many virtual interfaces or many interfaces of virtual machines mapped to the same NIC. So some NICs support 64 virtual functions, so that is virtualizations of the NIC. Some others support up to 128 functions. So you can connect multiple virtual machines to the same NIC. So you will get the capacity of that NIC distributed dynamically. So it will be still shared, but obviously you don't hit the bottleneck that layer 2 virtual switch is giving you. Usually OVS is around, or Linux bridges are about 1 gigabit per second of traffic. That's the regular throughput they can reach. But with SROV or pass-through techniques, you can go near the line rate of the NIC allows. And I keep mentioning pass-through this is just the difference is that you are not virtualizing. You are using this. You're not virtualizing the NIC. You are using the full capacity. I mean, a single interface dedicated to a single NIC. So supporting SRLB is not a dynamic thing that you can just enable. You need to specify at the BIOS level, at the BIOS level in the server, that you require this type of virtualization of the NIC, and also you need to configure the server with a specific NICs that will be used for SRIOB and how many virtual functions they will support. So it's a process of configuring SRIOB to have the server ready for using this kind of technique. And of course, these kind of configurations required a reload or rebooting the node. Comparing, okay, how to provision SRIOB in OpenStack and what OSM can do for you. Usually in OpenStack, you have to create a network that uses the given FISNet or physical network that is mapped to the NICs that you have enabled for SRIOB. So you need to configure this network manually. You need to configure the subnet of that network. You need to configure a port for that subnet or the network. And you need to launch the VM using that port. And then you need to repeat for every single virtual machine you need, or every single port in a virtual machine, at least from step 3, if you are sharing the same network. And also, well, when you expose an interface of a virtual machine to the physical world, you need to configure the physical switches as well. We will see more about that in the next session, but there's a lot of configuration involved. OSM simplifies a little bit this process. You just need to, obviously, in both cases, you need to configure the server. I mean, a one-time configuration. And then you specify to OSM, okay, the physical network that I'm using for SRIOB is called, in this case, in this example, FISNet2. And if you remember, we have been applying this to our vim create command because we will use it eventually in the next session. And once you have a vim enabled with SRIOB, then you just model your VNF to use this type of interface. So instead of VirtIO or Paravirt, you put SRIOB. And that's it. OSM will take care of creating a network, subnet assigning a VLAN, and creating the port and connecting your VMs to those ports. So it automates most of the process of having to do this. You just really model your VNF as you wish to, with the performance that you need, with the EPA settings that you need, and OSM will take care of everything. Even further, it can go and configure the physical fabric, I mean the physical switches that are located outside of your servers. But for that, we have a dedicated session where you will see which technique is used for this. It's a feature called SDN Assist, where OSM uses an SDN controller to configure the physical switches, the underlay network. Okay, but remember that in all cases, when you expose a virtual machine to a NIC of the server, where it's located, the virtual machine needs to have the driver of that specific NIC. Otherwise, it will not recognize it and will not be able to use it, and you will not see the interface enabled in your system. So how will we apply EPA in our network service? Taking into account that in OSM today, when you enable SRAOV, you are also enabling huge pages, CPU pinning, and assigning a dedicated node to your instance. That's how it's designed today. It's not granular. It's not that you can pick a single technique today. That is being improved in later versions to be able to test a single functionality. But since OSM is more tied to be used in real environments and in order to simplify things for the operators, then the first approach was to enable the complete thing to get the most performance when you use SRAOV or nothing, okay? So that's why if we select SRAOV today and you start configuring your VNF for SRAOV, you will notice that maybe one or two of you will be able to launch, and that's it. And that's because our huge pages pool in the servers at this moment is not big enough. So during launch, we will reboot the nodes to get more huge pages, and hopefully most of you can instantiate with SRAOV, okay? What we are doing then is taking this S1 interface between the packet core, access gateway, to the emulator, to SRAOV, and this will go through a data plane of switches instead of going through a virtual interface. So in the next session, I will talk more about how this will work and how SDN Assist will also help us configure the physical switches. So we're going to be able to see the whole thing. I mean, CPU pinning, huge pages being applied with SRAOV, and also the SDN controller configuring the physical switches. So how would this look like in our model in the VNFD? You have a guest EPA section that you can use inside the VDU section of the VNFD, where you can put these techniques: CPU pinning policy dedicated, for example, to use CPU pinning. That is, each CPU will be pinned and will not be dynamically distributed through the life cycle of the virtual machine. Mem page size, if you put large, then you are using the large or huge pages, and that's how it's called, pool of the server. Then, but this is not necessary if you are setting SRAOV. As I mentioned, if you enable an interface with SRAOV type, then these other things are implicit today. But in the future, we may choose to implement this in a way that you can just test CPU pinning or test huge pages or test SRAOV separately. Here, but for now, this is the presentation where I try to explain theoretically how to enable high performance in VNFs. In the hands-on exercise that we have after lunch, we will be able to experiment with these techniques.